All right, class, right? So statistics and probability is the second video. Not sure this one came up on the practice test, but basically the correlation coefficient is that letter R that we talked about when we did like scatter plots, and we did on Desmos. We added a table that like Y sub 1 is like, and then like a squiggly line, M X sub 1 plus B. Shouldn't have to make a table on the MCAS, but the correlation coefficient was that value of R, which just tells you how closely the line hits the data. And if you remember, anything where R was equal, like anything where R was about 1 or R was about -1, those were really, really strong. R is going to be 1 if it's a positive slope, and it's negative if it's, positive number if it's positive slope, negative number if it's a negative slope. But basically, if it's really if it's pretty close to 1, it's really, really strong. And if it's really close to -1, it's really, really strong. So like 0 is like the worst relationship ever because that's not really close to 1 or -1. So when you think about -9.91, that's actually really strong. That's really close to -1. And same thing, 0.87, that's pretty strong. That's pretty close to +1. 0.39 is not really close to 1, and it's not going to be like, it's going to be pretty obvious on the MCAS. So I would say that's a weak relationship. No relationship would be if it's like 0 or like really close to 0. So that was that one. A lot of you got it right, but basically the number of students here just correlates to like how many of the data points fall within these windows. So like these are kids' GPAs, and it's like how many kids have GPAs between 0 and 1. So on like your sheet, like on the MCAS, you had to drag this down. There's nobody with a 0 to 1 GPA. So you would have to drag this down so that it's like at 0, so it'd be like, that wouldn't even, it would just be like right there. And then between 1 and 2, you'd be like, all right, well, how many people have a GPA between 1 and 2? And it's really just this person and this person. There's only 2 people that have a GPA between 1 and 2. And then between 2 and 3, I see 2.2, 2.7, 2.4, 2.9, so that's 4 people. Right, and then between 3 and 4, I think was 6 people. So that's essentially what's called a histogram. It's basically like a glorified bar graph, but that's what it should look like. All right, the dot plot one here, not too bad, right? It's basically saying, you got female field hockey players and female basketball players and like their heights, right? So you can see there's a lot of field hockey players to the left part of the graph, so they're like shorter. It means you got 1, 2, 3, you got like 5 girls that are 62 inches tall, 2 girls that are 63 inches tall, 6 girls that are 64. Like you can just follow the heights along. Whereas basketball is much more spread out. So, in basketball, obviously there's a lot of girls that are really, really tall. So based on the dot plots, would a group appears at a larger average height? I think you definitely have to say basketball. Like if you average all these data points together, somewhere around here, average these ones somewhere here, obviously taller for basketball. Which group has a greater variability? So that's a variability. You might also see it termed as standard deviation. That was new last year, but it's still on the test for this year. And it kind of means similar things, like how spread out is the data, So like if you see all the field hockey players are kind of in this one area, whereas basketball spans a much larger area. So there's higher standard deviation with basketball, or higher variability with basketball, same thing. So you'd say basketball for that one. How many of the 12 basketball players are shorter than the tallest field hockey player? So field hockey player, the tallest girl is, boom, right there, 70 inches tall. How many basketball players are shorter than this girl? 1, 2, 3, 4. That's it. This fourth one, I'm going to explain a little bit, right? This one's a little bit heavier of a question, but we're going to go through it here. I just want to get the whole screen in there so I can annotate. But basically, right, so, you can make what's called a box and whisker plot with this data, but anytime you see quartile, basically it just means quarter. And median sounds like middle, it means the middle number. And that kind of stuff. Mode means the most frequent number, and then mean means the average. It's good to know that. It's going to pop up a few times on the MCAS. So mean is average, mode is most, median is middle. But quartile means quarters. So if you get data, you want to put it in order. That way you can actually figure out where half the data is. So I'm going to rearrange this data so that it's 1, 1, and then I think I have 1, 2, 3 twos, or sorry, 3 twos. And then I have 2 3s, 2 5s, and 1 10. right? So that's all my data. So with that data, you know, the median is like the middle number. Now I have an even number of data pieces. Like I got 5 on this side and 5 on that side. So the median would be like if there was a number in between the middle two. And then I don't have like a middle number. So with an even number of data, you don't have middle numbers. So you average those two numbers. You say the median would actually be 2.5, even though 2.5 is not a data point. But that's the median. Now quartile, same thing. If you ever split up the data in half, 50% of the data here, 50% of the data here. So quartile sounds like quarter. I'm looking for half of half. So this first half is my first half. So where's like the number that splits half of those? That's this. That's my middle number. So it's like half of a half. So the first quartile is 2. And similarly on the right side, I got 5 numbers. So where's the middle of those 5? That would be that 5 right there. So the third quartile is 5. The second quartile is the median, right? It's like second quarter, it's halfway. So that's the median. So that answers the first part, part A. And then part B says, what is the interquartile range? Well, these two numbers were the quartiles, 5 and 2, and the range is basically just the biggest number subtracted by the smallest number. So that would be 5, which is like the third quartile, minus 2, which is the second quartile. So it just means the range of numbers between here and here, between 2 and 5, is there's just 3 numbers. It's 3, difference of 3. So the interquartile range of the data is 3. And then you can explain basically what I just said in your words. And then part C says the value 10 of the data point is an outlier, which is absolutely true, right? That data point of 10 right there is like much higher than the rest of the numbers, right? But how does it affect the distribution of the data? Well, I mean, if that 10 was a 6, it wouldn't be an outlier, but it also would not have affected any of these numbers if it was 6. These all, the numbers would have been here, just you would have 6 here, but these wouldn't have changed. But what it would affect is what's called the mean, which is the average. So that 10 is going to create a higher average because you'd add them all up and divide by 10 for 10 different points. But adding a 10 versus adding a different number would make it a much higher average than it would have otherwise been. So that's how it affects the distribution. And then part D just says, if the number 10 in the data was replaced, so I got rid of the number 10, right? And I replaced it by the mode. So mode means the most frequent number, which if you look, I have 3 2s, and that's what I have the most of, right? So there's only one mode in this example, and it's 2. So if I replace 10 with the mode, how much will the mean change, right? So again, I'd still have 1, 1, 2, 2, 2, but then I'd add another 2, and then 3, 3, and then 5 and 5. That would be my new data. So basically, how would the mean change? Well, with the original set of data, if you added all those up, right, to get the mean, to get the average, you add them all up, divide by 10. I did it earlier. So when you added all those up, it would be 34 divided by 10. So the average would have been 3.4 with the 10. So if you took 10 away from it, 34 would change to 24. But we also added a fourth 2 in there, so it's plus 2. So it would really be a 26 divided by 10. So it would be a 2.6. So the average has gone from 3.4 to 2.6, not 2/6, which just means the mean changed by 0.8, right? So that's how you do it. And then quick explanation or just show your work. Get you full credit. We got probabilities. We just did this, so we can go pretty quickly with this one. It says the probability of X is 0.4, probability of Y is 0.6. Probability of both happening is 0.24. And then or, that's kind of a new one, but doesn't actually impact anything here, is 0.76. So fill in the blank. So event X and Y are, all right, so you got to figure out if they're dependent or independent. Remember, if it's independent, that means one times the other should equal the probability of both. If it's independent, multiplication gets you there. So 0.4 times 0.6, if you do that, that does get you to 0.24, which means these two events are independent. If it was anything different, then it would have been dependent, but they're the same, so it's independent. So it's independent because, what did we just do here, right? So 0.4 times 0.6 is point. So you'd say independent, and then you'd write down that line. That would be on the MCAS, like a scroll down option. You'd click it, and you'd select the right reason. That's that one. And then, might do a couple more of these, but this one has 3 parts. So basically it just says each student in a random sample of students at a local high school is categorized by gender, male or female, and whether they supported a proposal to increase the length of the school day by 30 minutes. All right. So what we have here is basically by gender and then whether or not they oppose it, support it, or have no opinion. So what is the probability of event A? A student of either gender, so male and female, supports the proposal, right? So how many people supported the proposal? Well, if I go to the support, there's 80, both male and female. So there's 80 people that supported the proposal out of a possible 200 people. So what is the probability? It would be 80 out of 200, right? If it was a calculator, you'd do it out, probably do it as a percentage. Actually, if you just cut them both in half, it's 40 out of 100, so that's 40%. But you probably have a calculator for it, so you get 40% either way. B, what is the probability of event B, a female student? All right, so we're given, like this is like probability given female students. Remember, that'd be like, now supports, that would be like probability of supports given female. So we're only looking at female students. So like, that's what it would look like otherwise, like the notation we use. But that straight line that means given. But even still, like if you're given the female, we're going to only restrict our data to these 90 females here because that's all we're doing, right? So a female student supports, well, out of the 90 female students, 40 of them support it. So in that one, you would say a 40 out of 90, which again, if you got it in your calculator, would be 44%. And so the last question just says, are these two events conditional? Which means, does one rely on the other, or are they totally independent? Well, if the probability that anybody supports it is 40%, but the probability that female support is 44%, this is a different number than 40%. So that means that if your gender is female, you are a little bit more likely to support it, which means they are conditional, right? So they are dependent. It's not independent, right? So that would be like a yes to part 3. Yes, they are conditional. So frustrating. All right, so on this one, guys, these answer choices are all wrong for number 7. It should say 10.7, 10.6, 10.5, 10.4. You know, so it says, you know, estimate the gold medal finish time for 1940. So you're looking at the line. So if this is the years after 1900, I'm going to go 40 because that's 1940 is 40 years after 1900. And if I follow that up, I can see it's like, you know, it's like right there, which is about 10.5. So it should be C, even though it says 9.5. Meant to read 10.5. So sorry on that one. That one you're going to do on your own. You'll be okay. And then just the last one is probably the last one I'm going to cover in the video. But, you know, which of the following statements are true? So you have 2 data sets. Now, I know this is not on your sheet, but I do want you to copy down the data sets onto your sheet and then answer the question. But ultimately, when you do it, 10, 11, 12, 13, 14, those numbers are really close to each other. 2, 3, 7, 11, 18, 21, they're a little further apart, which means data set 2, D is definitely true. They definitely have a larger standard deviation. They're more spread out. They're more variables, same thing. So that's D is correct. I think if you add all these up and divide by 5 and add all these ones up and divide by 5, I actually think you get the same answer. I think the answer is 12 for both. So I think A is also right. They also have the same average or same mean. So you could do the rest for homework or for classwork if you have time, and that's it. Good job.